Assalamu alaikum warahmatullah. Today our class actually is to continue the previous topic, which is the designing of parallel programs or designing parallel programs. This topic actually is a little bit complicated compared to the previous topics, because this one is more practical, more close to the real tasks that you have to do. Okay, so at first we learned how to make the programs parallel. So we learned two ways. So the first way is manual by the programmer. The second way is automatic by using some available tools. Okay, then after that we learned about the advantages and the disadvantages. Guys, before I continue, did you see my videos on YouTube? Guys, hello.
Which one, doctor?
Yeah, I uploaded some classes 2 days ago. Did you check them?
I saw them, but I haven't watched them till finish.
Uh-huh. Okay, at least you know that there's something on the YouTube. Okay.
Okay.
I try to because we have two classes need to be replaced. I recorded I 2 times. I promise you to upload classes, but unfortunately, in the 2 times I had technical problems. So one time I have no audio at all, so I have to repeat the class, and the second one we had technical issue on my computer, so I couldn't continue that. I couldn't finish properly. The screen was black, totally black, after I opened the record. So I have to repeat these two classes, inshallah, and I upload them as soon as possible. Because as you know, we are very busy. That's why we don't have enough time to do all of that stuff. Okay, guys. So sorry for that. Especially the important
It's,
class is the one that we discussed last time about the how to create the threads, how to establish them, and how to solve some issues. Yeah, that's the thing. And the other one is how to calculate the cost, how to calculate the efficiency, how to calculate the overhead, and so on. Both of them are very easy because I explained them many times, but for referencing, I need to put the video on the YouTube, inshallah, as soon as possible. Okay, as we said here, we have some advantages in the automatic way. I mean, for the automatic approach, and also we have some advantages with the manual approach. But both of them, we cannot say this way is perfect or that way is perfect. It depends on the requirements. So if you don't have enough time to make it parallel, much better and easier to use the automatic tool. If you have enough time, you have enough resources, you have enough team, and this program is, I mean, worthy to make it worth to make it parallel, then you go definitely for the manual way to make it, I mean, properly parallelized. Okay. Then the second step here we have taken is the understanding of the program or the existing program or I mean the problem that we are trying to solve. Okay, so this is the merit actually of the whole process. So if we cannot understand carefully the problem and how it works and how it should be solved, in that case, we will never be able to succeed of making it parallel in a good manner. Okay, so that's why it's very important. It's very important, guys, to understand the nature of the problem, how it's working, how we should fix it or solve it. Okay. Then, in terms of, I mean, in this regard, what we need to do at first, we need to make sure that the problem is parallelizable. If parallelizable, we continue. If not non-parallelizable, then we stop. in that case, we cannot make it parallel. So even if we try to make it parallel, the thing will become worse. Okay, so the second step is to identify the hotspots in the program. So hotspots means the heavy functions or the heavy areas of the code that has a lot of tasks, a lot of complexity, a lot of time wastage, and so on. So that's called hotspot or bottleneck. So we have to identify where is the hotspots and the bottlenecks. Then we have to focus on them and change them to a parallel piece of code. Okay. Then after that, we came to the partitioning. Partitioning actually is very simple. Partitioning is two types, the domain decomposition and the functional decomposition. Domain decomposition is, if we remember the example of the university staff salary calculation. So if we divide or do partitioning based on the domain, then we maybe the first partition will be the academic staff, and the second partition will be the non-academic staff data. Okay, so we have two chunks of data, then we send them to the same function. I mean, we send these two copies of data to two copies of the same function. Then we calculate the salaries for all staff, but in different two groups. Okay, or three groups or four groups, depends on the problem, depends on the business that we are trying to solve a problem in or for. Okay. The second way is the functional decomposition. So for the same example of the salary, here in this case, maybe we don't divide the data into multiple groups, but maybe we divide or partition the program itself into multiple functions. So every function could work separately at the same time, maybe along with other functions. So for example, we can create function that calculates the tax and another function that calculates the allowances. Then we give them the data of the staff, and they will calculate their tasks, or they will accomplish their tasks based on the functionality at the same time. So the first function will continue calculating the tax for all staff, and the second function will continue at the same time calculating the allowances for all staff. So we have two functions in parallel doing some calculation for the same data. So in this case, this is called functional decomposition. Also, we can make it hybrid. So it could be domain and functional decomposition at the same time. So maybe we split the data into multiple chunks. Then also we divide the functionality into multiple functions. Then we make a lot of copies of the functions. Then we use that functions on different data at the same time. And it will be at this moment, it will be a hybrid decomposition. Okay. Okay. Then we came here to the communication. This is the last week. So in the communication, we said who needs to communicate. Then we said that the tasks sometimes need to communicate, especially the tasks that relies on each other. Okay. Sometimes tasks are fully dependent on each other, and sometimes they are fully independent on each other. So if they are fully dependent, then the best way is to be sequential. But if they are fully independent, this is the optimal way to make parallel program. So parallel will give the best result if all tasks are independent on each other, independent from each other. Okay, so this is the optimal environment or the optimal scenario that makes the best result of a parallel program. But in most cases, the tasks are not fully independent. Sometimes they are partially dependent. So sometimes some tasks can run independently, but at some point, at certain point, they have to wait for each other to do kind of synchronization. Okay? So in this case, okay, guys, I will give you a very good example, very simple example. Okay, if let's say we have a car race. Okay, suppose that we have car race like that, but we have two parts of that race, two parts or two stages. So maybe the first stage is for example 10 kilometers, and the second stage is for example acceleration. Acceleration computation. So here for this stage, what we need to calculate, the acceleration of the car. So here the first stage we put two cars, for example, or three cars that are going to compete with each other for the first stage. Then after that, we have to use the same cars here. After they finish the first stage, we have also to use them for the second competition here. Okay, but the rules of the racing is to start all cars at the same time, right? So for this certain point here, certain point here, I don't know what. Here we have to do a kind of synchronization here. Okay, this is what they call it, synchronization. Okay, so in this at this moment we have to wait. So the second competition will not start unless all the three cars arrive at the same or at the beginning of the second stage. Is that clear, guys?
Yes, doctor.
Yes. So for this case, in this case, if let's say this car arrives here and the second car maybe is here, and maybe this car is very slow and this car still here. So when this car passes the line, is it able to continue the second stage? It's not able, right? Until the second car then arrives at the same at the start point of the second stage, and also the third car arrive at the start point of the second stage. So what does it mean? This means this one is task 1, for example. This one is task 2, and this one is task 3. So task 1 cannot continue the second step until all the cars or all the tasks finish the first stage. Okay, so in this case, maybe this because they need to rearrange maybe the tasks. For example, this task is here, so maybe task 2 arrives first. Maybe task 2 arrives first here. Okay, so in this case, if task 2 arrives first, then they have to put it here at the first. So maybe it needs to be tested first. So it depends, maybe the order it changed. So sometimes it depends on this result here, the result at this moment of synchronization. We have to make a decision, for example. Maybe we need to find, maybe we have three employees, then we calculate their salaries in different tasks. So maybe the employee 1 in task 1, employee 2 in task 2, and so on. And at this point here of synchronization, we need to find which one has the lowest salary, for example. So then, based on their results of the 3 tasks, we need to compare, right? So we cannot find which one is the lowest salary until we get the results from the 3 tasks. So in this case, we have to wait. We have to do a kind of synchronization. So here we have to use some one of the existing techniques. So maybe we have to do like looping. Maybe we use while loop, like the while loop that I give you in the example for the assignment. In the assignment, you see we have a while loop that's designed to wait for all tasks to finish, right? And once they finish, the result will be printed. Okay, so that's what they call it, synchronization. And sometimes synchronization have to be done on the level of variables. So if, let's say, we have to do synchronization because we have multiple tasks that changes the value of a certain variable. So when for example task 1 start to update the variable x, for example, it has to look it for writing first, then after it finish writing, it unlock that x variable, so it will be accessible for accessible to the task 2 and task 3, for example. Okay, like that. Suppose that this is a variable x. Okay, and here, for example, when the task finish, for example, arrives at the end line, it need to check the value of the variable x. So at the initial time, it's 0. So if the value, if let's say we need to find who is the fastest, for example, who is the fastest. So maybe task 1 need to save the speed here or the time here. Then after that, when the other task arrive also at the end line, it need to check if its time is less, maybe it need to override, or maybe if its speed is faster, it need to override the value of x. So in this case, we have to, what to do here? Where's the brush? Yeah. When we want to write here, we have to do lock. So nobody can change this value. So if this guy try, it will give not an error, but it will take it into, if let's say at the same time, the second task try to update the value of the x, then it should go through a waiting loop. Okay, so this is what they call it, look and wait. Look and wait. Okay, once this one finish, this one also will stop waiting and will get the ability, or will get the permission to access that variable and change it. Okay, guys, is that clear? Okay.
Yes, doctor.
So this is what they call it, communication. And sometimes this task 2 need to send some data to task 1. So how they can send that data or exchange data? They use the shared memory. So normally we define some variables and we use them to share or to exchange data. So for example, this task 1 is always trying to find which one is the fastest one, for example. Or maybe there's another task here, for example. Sometimes we have another task outside, another task which is called the main task, for example. TM, for example, main task. So maybe this main task is always reading the value of the winner, trying to find who is the winner. So once the T1 arrives, maybe the value or the ID of the task will be saved here, or maybe the car plate will be saved here. Then the main task will get the value or the car plate of the winner, and maybe it will show like maybe we'll celebrate or something like that. We'll do something else. Maybe we'll fire some fireworks or something like that. Okay, guys, is that clear? So in this case, this is called shared memory, and here this one is called shared variable. Shared variable between the multiple threads, okay, or between the multiple tasks. So this is a very common kind of communication. Okay, some people are calling it like shared memory. Some people they call it callback. Some people there's many names actually for that. But the concept is very easy. They define some variables, and that variables will be updated, will be read and written by the multiple tasks. Depends on their needs. Okay, so in that case, what we have to do is to do access control for that and synchronization. So we have to implement some techniques like semaphore or looks or whatever, or some techniques like look and wait. Yeah. So we have discussed the factors that need to be considered. One of them is the cost of the communication. So the cost of the communication should be less than the cost of the calculation. Okay. Otherwise, if the cost of communication is higher than the cost of calculation, then it's better to keep the program as sequential. Okay, or in sequential mode. The second thing is the latency and bandwidth. Latency must be low. Bandwidth should be increased. But the bandwidth shouldn't exceed the maximum available bandwidth. Okay. Then here we have the visibility of communication. We have talking about this synchronization and synchronous and asynchronous. This one also I explained last week. And we have scope of communication. So we have some types or scope of communication, which is point to point and the collective. So we have here the broadcast, which is one-to-many, which sends the same copy of information to the others. And the scattering, which is sending multiple different data from the same point to another, or from one task to multiple tasks, but every task will get different information, depends on its need. Then we have the gathering. Gathering is to gather different information from multiple tasks. Then we have reduction, which is to calculate the value of the results that's received from multiple tasks. Okay, then we have efficiency here, efficiency of communication. So the efficiency of communication, we have to increase it. How to increase it is by reducing the cost, reducing the time, reducing the overhead and everything. Okay, then we have the complexity. Complexity and overhead actually are very important here. So we should always try to make our things or our programs as simple as we can. We always target to reduce the complexity as much as we can. And also the overhead is not a good thing. So that's why we need always to minimize it as much as we can as well. Okay. That's all about what we have taken in the last 2 weeks. So today we are going to talk about the synchronization. So here we have types of synchronization. The first type of synchronization is what they call it barrier. So usually implies that that all tasks are involved. Okay. Each task performs. Let me read first. Each task performs its work until it reaches the barrier. Okay. In this case, the barrier actually is like this. This is what they call it barrier. Okay. So we have a certain point that that the multiple tasks need to stop at it. Okay, this is what they call it barrier. Okay, so each task need to perform its work until it reaches certain point of achievement. So for example, in the what they call it in the car race, when they reach to the final line or the end point of the competition, they have to stop and wait for the others. Okay? When the last task reaches the barrier, all tasks are synchronized here. That's what they call it synchronization. So here, if task 1 arrives first, then it need to wait for task 2. It need to wait for task 1 and task 3. When task 1 and task 3 arrives at the start point of the second stage, at that time we can say that all tasks are synchronized at that time. Okay, at that point of time or at that point of barrier. Okay, so the barrier actually is a point of synchronization. What happens from here varies. Often a serial section of work must be done in order. In other cases, the tasks are automatically released to continue their work. Okay, so here, after they arrive here, okay, and after all the tasks are synchronized, so in this case, like this, and this one also. So at this moment, they are synchronized. Here, maybe to test the acceleration, what they need to do is to test car by car or car after another. So maybe they start task 1 first, then after task 1 is tested, they go to car number 2. After car number 2 is tested, then they go to car number 3, and this is what they call it sequential or serial work. Okay, and also sometimes they are allowed to start at the same time. So maybe this one is not acceleration test. So maybe this one is another stage which is 100 kilometers, for example. So at this time, what they need to do, they need to check here the main thread or the main task need to check for all tasks to be synchronized first. Then after that, it will tell them to start. So it will need to trigger them again to start to work in parallel or concurrently. So that that task done by the main thread actually is done in sequential mode. Why? Because the nature of the checkpoint here is sequential. Okay, so what they need to do, task number 1, here for the main thread, it need to make sure that all tasks are synchronized. This is the first task. Okay, first task is to check synchronization. The second task is to trigger tasks one by one, right? Or maybe it would trigger them at the same time. It could be also. But anyway, even if we have only these two steps actually by nature are sequential. So there is some part or some kind of work that should be done in serial or sequential manner at the better point. Okay, guys. So here they said often a serial section of work must be done. In other cases, the tasks are automatically released to continue their work. So sometimes they have something called self-check. So that tasks depends on some shared variable. They have a self-check. Okay, so they don't need to be I mean controlled by the main task or something like that. So in that case, the part of serial work is sometimes not there. Okay, so it's not necessary, it's not always to have a serial part of work. Okay, types of synchronization. We're still in the same topic. So here we have what they call it look and semaphore. So look or semaphore actually is the same thing. Look or semaphore is the same thing. So here it can involve any number of tasks. Okay, so normally the look is used for shared variables in the memory. So if let's say one task wants to update the value of that variable, of that shared variable, then before it update, it should look first the variable, and after that it update, and after it finishes updating that variable, it need to unlock to allow others access that variable. And this way, I mean, controlling this looks or semaphores actually, or mostly, is done automatically by the compiler. Okay, so maybe the programmer need to only write something like this. So if let's say we have x variable in the memory, so let's say task one wants to save value 5 into the x. Okay, so what they need to do is to write something like that in some programming languages. So they have to write something like this. Then they say x equals 5, like that. So the other tasks or the compiler will understand that this one is a look. So x cannot be accessible by other tasks. Only T1 can update. Once T1 finish, so once the compilation comes to here, or the cursor comes to here, then the other tasks will be allowed to access the same variable. Okay, so it's so simple, so easy to implement. You know what's the semaphore, guys, right? What's the meaning of this word? Anyone knows? What's the meaning of this word in English?
I think it's a non-negative value.
No. Semaphore is exactly the traffic light. You know the traffic light?
Okay.
Yeah, this is a traffic light. In many countries, they call the traffic light, they call it semaphore. Even in my country, we call it semaphore. We don't say traffic light. Okay, so
Cool.
this is exactly like the traffic light, exactly. So the way is to open one side of the road to some cars, then the other cars will be stopped. The other sides of the conjunction will be stopped, right? So until we finish, we give them a portion of time, or maybe until the cars are finished. Then after that, we stop that side, we open another side of the conjunction, right? So this is what they call it, semaphore. Okay, exactly like the traffic light, the semaphore can work. So it will stop some tasks from accessing the X or the variable. So the variable here is the conjunction or the road, and the cars here are exactly like the tasks. Okay, so here the lock and semaphore are exactly the same thing, so they can involve any number of tasks. There is no limited number or certain number of tasks that's allowed to use the same lock. Okay, you can use lock for like 5 tasks or 100 tasks or 2 tasks. It's up to you. It can work for unlimited number of tasks. Typically used to serialize, protect access to global data. So when we have global data, which is the shared memory variables, we have to protect the update or the writing process on that variable to make sure that all tasks can get their job successfully done. Okay, so here to protect access to global data or a section of code, only one task at a time may use or own the lock. Okay, so once one of the tasks initiates the lock, the others have to wait. Other tasks have to wait until the task finish. So when that task finish, the others will compete. So the fastest who can make the lock or can establish another lock will own that variable. Okay? Then the first task to acquire the lock sets it. This task can then safely serially access the protected data or code. What does it mean safely? Because in many cases, especially the new programmers, if a new program is trying to make a parallel code, what will happen is that, so if let's say this task, or this is a variable X, which is equals to 0, like that, then here we have task 1. So this task 1 calculates summation of 1, for example, to 100, like this, and after that it need to do like X equals the previous value of X plus the summation. So let us say here Y equals the summation of this. So here we can say X equals X plus Y. Okay. So in this case, this task need to read the value first of the X, then after that it adds the value of the Y to it to update the X, the new X, right? What's about the task 2? Suppose that we have task 2 also, and task 2 calculates like from 101 to 200, for example. Okay, so is that clear, guys? Is this clear?
Yes.
Okay, so this is very important, guys. Okay, please pay attention. So this is the second task, and this is the first task. So every task is running in different thread, and both of them are running at the same time concurrently. Okay, so if let's say we don't implement the lock and wait, what will happen here if the two tasks read the X at the same time? What will happen? if they read the x at the same time, what will happen, guys? The first task will do x equals 0 plus, for example, y, right? Suppose that y is, for example, 2589, for example. Okay? Then here, the second one also, when it reads the value of the x, it found it 0. So in this case, suppose that the value here is like 95325, something like that. What will happen here? What will happen here? The result of x is not correct, right? Right, guys, or not? Oh, you are not with me. Guys,
Here, doctor.
Yes,
are you with me?
Yes, doctor.
doctor. Yes,
Yeah.
doctor.
So
doctor.
what will happen here? What will happen here? The result will be wrong, right? Suppose that the summation of 1 to 100 is equals to 2589, and the summation from 101 to 200 is 95325. Suppose that, okay? So here what will happen, both of them read the x variable at the same time and they found its value is 0, then they will update it like that. So if, let's say, this one, the writing process of the second task was finished at, I mean, after the first one, then the value of x will be this, right? The value of x will be this only, okay? And this is only the value of the, or the summation of the second task, the numbers at the second task. While what we have to do is to check whether the value of the x is I mean, to read the value of the x first, then we add the summation value that comes from a certain task. Then after that, we have, in the second task, we have to check whether the x is in use, locked or not locked. So if locked, then we have to wait. So in this case, if, let's say, the task number 1 tried to access the variable x first, then it decided to lock it. So task 2 cannot read the x while task 1 is updating, right? So in this case, what will happen? What will happen here? The result will be correct, because here this task 2 will stay waiting until the task 1 finish. So here here what we have to do is to change this. Actually, I don't know what happened to my mouse. Okay, so in this case, the value of the x in the memory will be changed to, like that, 2589 first, right? Then after that, the second task here will read the value of the x. It will find it 2589. Then it will plus the what they call it, 95324. Okay. So in this case, the result will be updated to the x. So both of them will work successfully, and the result will be correct. Is that clear, guys? I tried my best to simplify it, because if the access or the shared variables are accessible at the same time by multiple tasks, then they can be updated at the same time by multiple tasks, especially if they try to write a different value on the same time to the same variable, then that saved value will be sometimes wrong, totally wrong. Okay. So suppose, for example, I will give you I will give you a certain example in different way using the same scenario here. Suppose that task number 1 wants to make this. wants to make x equals to 0, 0, 1, 0, 1, 1, 0, like that. How many? Yeah, like this. This is 8, right? Suppose that the task number 1 wants to save this value to the variable x, and also the task number 2 wants to make this. For example, 1, 1, 0, 0, 1, 0, 1, 1, for example. So the result, if they try to access or to write different values on the same variable at the same time, maybe the result, it will be a combination between both of them. So it may be like this 1, 1, 1, maybe it will combine all ones together, for example, and the result will become like that, which is totally wrong, right? Because two tasks are trying to save different values to the same address of the memory, right? So sometimes this is what happened. For example, task number 1 saves value of 5, and the task number 2 saves, for example, 10. 5 and 10 together sometimes gives something like 12 or 7 or something like that, which is totally different than the original or the intended values that we meant to save in the variable. Okay, guys, is that clear?
Yes.
Okay.
Yes, sir.
Other tasks can attempt to acquire the lock, but must wait until the task that owns the lock releases it. So once a variable is locked by, for example, task 1, so task 2 and task 3 have to wait until task 1, the owner of that existing lock, released it first. After it's released, then the other tasks could access the variable. Okay. So it can be blocking or non-blocking. This is quite subjective, actually. I don't know how to explain this to you. Do you know what's the meaning of blocking and non-blocking? Last week I explained this, right? What we have here, we have something called blocking and non-blocking, right? So blocking and non-blocking, and blocking is this thing actually is under the synchronous and asynchronous communication. Okay, so things that are synchronous, it's normally blocking. But if the communication is asynchronous, so it will be non-blocking, right? So here, where is it? This one. Oops. Okay, here. So how it could be blocking or non-blocking, because this one is synchronization, right? This one is synchronization. So based on the previous slide, so maybe you think that if synchronization, it means blocking, because that one we learned that the synchronous is blocking. But synchronous doesn't mean synchronization. The synchronization is the name of the operation. The name of the operation to protect the shared memory, or to make sure that the data is always at any time of at any point of time is correct. Okay, this is what they call it, synchronization. But sometimes we do synchronization, but the tasks by their nature are not blocking, are not synchronous. Why? Because their tasks are the size of their tasks are different, so it's very rare to get to the same point at the same time by multiple tasks. So this depends on the nature, guys. So if this is the nature of the application, then it could be non-blocking, because based on the nature of the problem, we never see any task is waiting for the others even though we implement locks. Okay, because they reach the same variable in different points of time by nature. So in that case, it could be non-blocking. But if tasks could reach the same point of or the same data at the same point of time, so in that case it will be non-blocking. So when the synchronization is non-blocking, then here we will have no waiting time. I mean, no time wasted for waiting, because here we cannot see any task waiting for the others. But if blocking, we will have a lot of wasted time for tasks to be waiting for other tasks. Okay, guys? Then here we
Okay,
have
okay.
synchronous communication operations. So involves only those tasks executing a communication operation. When a task performs a communication operation, some form of coordination is required with the other tasks participating in the communication. Yes, definitely, that's 100% sure. Once the things are, the tasks are using the same data, which is shared in the memory, then there have to be some kind of coordination. Okay, so there's supposed to be some kind of coordination between those tasks. So the coordination should be the responsibility of some part of the program. So maybe it's the responsibility of the compiler, or maybe it's the responsibility of the main task, or something like that. So the coordination is supposed to be there. So in our example, the one that we build the assignment on, the assignment that I give to you, we have coordination, kind of coordination, but that coordination is done by the main task. So the main task implements what they call it while loop to wait for the other tasks to finish, right? Let me wait for this. I don't know why my Visual Studio is becoming like that. It's not responding. I think I need to reinstall it. It was a long time. I think it's 5 years. I didn't update it. I didn't, format my laptop. That's why I feel it's like very heavy now. Okay, anyway, we discussed before while it's loading. Okay, so here the coordination is supposed to be done by somebody. So it could be done by some tasks, or could be done by the compiler. Depends on what you are doing. For example, before a task can perform a send operation, it must first receive an acknowledgement from the receiving task that's okay to send. Okay, so this is kind of coordination. So maybe the sending function need to wait until it get an okay message from the receiver. Okay, so this is what they call it. This is one example of the coordination. So discussed previously in the communication section. Yes, we already discussed that before. And here, let me delete something first before I. So slow. Okay. Okay, this is the program. So what we have here is that we have a main task that runs other tasks, right? But here in serial. I don't want to show you the parallel part because this is your assignment. So here, this task, the main task, call the other tasks in different threads. Then after that, it waits for them to receive or to prepare the results. So the primes should be found, the odds should be found, and the evens should be found in order to be able, in order for the main task to be able to print the final results. Okay, so this is a kind of cooperation that's done in parallel programs. Okay, any question, guys, before I move?
No.
Okay. In C sharp, actually, in C sharp, if for example want to make look, for example, if you want to make a look, so here, hello, guys, are you still with me? Are you still with me, guys? Hello, 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 guys. Hello. Hello. Hello, guys.
Yes, doctor. Yes,
Yeah,
doctor.
are
You
you
are
still
talking,
with
man.
me? Yeah, actually I
Yeah.
forgot to switch on the charging switch. I mean charging adapter. I forgot it off. I lost my battery. Okay, so for example here, if let's say you want to change this value for this variable, so what you need to do is to implement a kind of look like this. So what you need to do is to look the variable first, like that. Then inside the look body, you can change it. You can change its value. Okay, this one, because this one is a Boolean. So Boolean, I think, has some restrictions. Okay, anyway, let us, we want to change, let us consider that we want to change, for example, the primes variable. Yeah, like that. So the primes variable will be something like that. You see, it works. So if we run this loop, this task actually is not going to change the value of the primes until it's locked. Then, while it's locked here, the other tasks cannot update it, cannot even access it. Okay, guys? This is how the lock could be implemented. Very simple, guys, right? Doesn't require a lot of things to do. Okay, so that's all about the synchronization. Then what we have here is the definitions. So a dependence exists between program statements when the order of statement execution affects the results of the program. Okay, so if let's say we have two tasks. Let's say we have two tasks. Let us go back to the paint here. So let us consider the example of the what they call it car race here. Suppose that the car that lost that's loser, considered a loser in the first stage, actually is not going to attend or to participate in the second stage. Okay, suppose that. So if let's say the car number 3 is a loser, so in that case the computation will be between the first and second cars only. So here what happens, the result of this task affects the result of the other tasks, I mean, or affects the result of the whole race, right? Right, guys? So in this case, this is what they call it dependent, because here we have some kind of dependency. We have a kind of dependency. So some tasks, the result of some tasks affects the result of other tasks, or maybe a result of one task affects the entire result of the whole program. So here, if let's say car number 3 is loser, then the second race stage actually is going to be between car number 1 and car number 2. Okay, what if the car number 2 is a loser? So in this case, the second stage will be between car number 1 and car number 3. You see here the result of the program actually, or the result of the computation, is depends on the result of the tasks, right? So the result of task 3 will affect the entire program. Result of task 2 will affect the others, and so on. Okay. So this is what they call it, dependence. So that is dependency only. Dependency, which means program depends on another program, or maybe sentence or program statement depends on another program statement, or maybe program part depends on another program part. There's also something called data dependence. Data dependence. So here in this case, a data dependence results from multiple use of the same location in storage by different tasks. Okay, the best example for this is our program actually. Our program here. So this main task actually is going to establish or going to trigger the threads that need to calculate the primes, evens, and odds. Okay. Then after that, it needs to wait for this data to be available, right? It needs to wait for the data to be available. So this is what they call it, data dependency. So here the main task depends on the data, the availability of the data to continue its task and finish, right? So if the data stay not available or does not come to quickly, then the program have to wait for long, right? Or maybe if the one of these tasks fails to get the result or fails to finish, then this main task will stay waiting for forever, right? So this is what they call it, data dependency. Data dependency. Dependencies are important to parallel programming because they are one of the primary inhibitors to parallelism. Dependencies actually are inhibitors of parallelism. So their existence in a program will cause a lot of delay, or maybe sometimes causes an unnecessary waiting time, or maybe causes unnecessary wastage of resources or something like that. But unfortunately, we cannot get rid of them. We cannot get rid of them. So at least in one parallel program, at least we will have 1 or 2 dependencies, at least, okay? Because here, as I said, every program, even if that program is parallel, it have to start in sequential mode, right? It has to start in sequential mode first, right? So here, sequentially, we call the primes up to, then after that, we call the events up to, then after that, we call the other function, which is the odds up to. So this initiation of the functions or the threads is going have to be in sequential mode. We cannot establish all of them at the same time, at the same moment, cannot. So this is one of the this is also a kind of dependency, because the second one cannot be called unless the first one is called, right? Because this is the sequence. Then the second thing here, to wait for the result, to finalize the program. So here we have 2 dependencies in this program, and we cannot get rid of them. There is some techniques that can help to get rid of this kind of dependencies, but that techniques are possible to be used only for programs that are fully independent, for tasks that are fully independent. So instead of printing the result here by the main task, so maybe we can allow each task to print its own results. Okay, we can allow each task to print its own results. So in this case, we don't have to have this kind of while loop. We don't have to wait, and also for other tasks, they don't have to wait for example, task 3 doesn't have to wait for task 1 to finish. So maybe odds are very fast to be found. That's why they finish first. They finish first and they print their result. Then after that, it could be the primes. Then after that, it could be the events. So each function finishes, it can print its own result. So in that case, we will get rid of the dependency. Okay. This is, as I said, it's not always possible, because sometimes depends on it. It's fully dependent on the nature of the problem. So if the nature of the problem is fully independent, then we can get rid of any type of dependency in the program. But if the nature of the program is partially dependent or not fully independent, so in that case, we have no choice. So we will have to have at least 1 dependency in our program. Okay, guys, these things are really subjective. So we cannot get like one rule or one standard to say when we have dependencies or not, because it depends on the scenario, depends on the nature of the problem. Okay, guys. Okay, here examples. Example number 1: loop carried data dependence. Okay, so here, do 500J equals my start, my end. Okay, the value of AJ minus 1 must be computed before the value of AJ. Therefore, AJ exhibits a data dependency on AJ minus 1, right? Because this one is the item, actually the A is item, J minus 1 is the index. So if, let's say, you want to calculate the item number 3, you have to calculate the item that's before it. the item number 2 times this value, right? So here, this item cannot be calculated unless this item is calculated. So this item is fully dependent on this item, right? Is that clear, guys, or not?
Yes, doctor.
Yes, doctor.
Hopefully. Sometimes I feel like you don't tell me the truth, because I feel like maybe you are very smart, or maybe I'm very bored. You just want to finish this class, or I don't know really. So sorry to say that, but this is a normal thing actually. Okay, 1, 2, 3, 4, for example. If let's say we have these items in an array like that. So if let's say the array name is A, so in this case, this one is A1, right? And this one is A2. This one is A3, right? And this one is A4. So the rule of this actually is like that. A2 equals A1 plus 1, right? And also A3 equals A2 plus 1. This is the rule, right? Yeah, so here, in order to calculate the item number 3, we have to calculate, or to get the value of the item before it, which is the A2. So this is what they call it dependency, okay? I don't want to go through all of that stuff, because these things sometimes make it more complicated. I try to simplify it using simple examples here on the paint. So I hope that you already understand. So this is very clear, right? So AJ depends on AJ minus 1. This is what they call it dependency. And AJ cannot be calculated unless the AJ minus 1 is available. Okay? Loop independent, data dependent. Loop independent, data dependence. So here, as you can see, as with the previous example, parallelism is inhibited. The value of y is dependent on distributed memory architecture if or when the value of x is communicated between the tasks. So as you can see here, the value x is used in the both tasks, right? So the first task will make the x equal to 2, and the second task will make the x equal to 4. So here in this case, the loops are dependent. The loops are independent on each other, but they are dependent on the variable. Okay, they are dependent on the x value, right? So shared memory architecture, which task last stores the value of x. So if let's say the task number 2 changes the value of x first, then task number 1 changes the value of x later, then here the x value that's used in here and here actually is going to be the last one, based on the last update, right? So this is what they call it data dependency. Even if the loops are independent, but they are still dependent on data. So although all data dependencies are important to identify when designing parallel programs, loops carried dependencies are particularly important, since loops are possibly the most common target of parallelization efforts. Okay, I'm not going to explain this because this one is 1,000 times we explained that. Okay, loops are the main point, the main hotspot that need to be optimized, that need to be parallelized. That's why we have always to take it into account. Okay. How to handle data dependencies, distributed memory architectures, communicate required data at synchronization points. So the solution is to use the distributed memory architecture with a synchronization points, or shared memory architecture with synchronized read and write operations between the tasks. So in order to do this, you have to implement semaphore or look. In order to do this, you have to implement something called barrier or something like that. So there are a lot of techniques in this course. Actually, you are not required to understand all of that stuff, but even though this is not required by this course, I intended, or I tried to let you really make your hands dirty with the code. Okay? So I tried to let you touch the code and see how to initialize, at least for a simple scenario. Okay? How to make things in parallel, even for a simple scenario. At least you have an idea in your mind. I don't want it to be all 100% theoretical. Okay? Then we have load balancing. Load balancing actually is very important. So load balancing refers to the practice of distributing work among tasks, so that all tasks are kept busy all of the time. So it can be considered a minimization of task idle time. So load balancing is important to parallel programs for performance reasons. For example, if all tasks are subject to a barrier synchronization point, so the slowest task will determine the overall performance. Okay, guys? So if let's say this is 3 tasks, so the red line here, or the red color, is the ideal time for the processor. So at this time, at the red point here, the processor is doing nothing. The task is only waiting for other tasks to finish to reach the synchronization point, or the what they call it, the barrier line. Okay, so this task 1 already finished here at this moment, right? So task 1 is the fastest one, but because task 2 is slower and tasks 3 and 4 are more slower than the task 1, task 1 have to stay idle waiting for the other tasks to finish, and practically it will finish here at this line. Okay, so the red areas here are wasted. How to minimize the wasted resources here is by distributing an equal amount of load, or equal amount of workload among the tasks. So if we make the tasks, or if we distribute the tasks fairly, I mean equally to the processors, they will finish at the same time, maybe at this line here. So the waiting area will be less, right? The ideal area will become less. So if the red area become less, then the resources will not be wasted. As you can see here, the red one is wait and the blue one is work. Okay, so this is what they call it, load balancing. Okay, let us go back to our example of the salary, university salary. Remember that example, right? I said that day, I said we can do what they call it, decomposition of, or partitioning of the data into academic staff and non-academic staff, right? We can have 2 groups, right? So what if we calculate the salary here? We will calculate the salary here. Depends on the 2 groups, right? Suppose that the first group has only 100 academic staff and the non-academic staff are 2,000 or 20,000. Let's say 2,000. So what will happen? this task could finish in like 1 hour, for example, and the other task, it may need like 5 days or 6 days. So while this is still calculating, the other one is idle, right? And the resources are wasted. So what we have to do in this case, we have to make it balanced. So instead of 100 here and 1000 here, so maybe what we need to do is to make this 1000, for example, 1050, and this one also 1050, because the total is 2100, right? So if we make it that way, then we cannot say these groups are academic and non-academic, right? This is totally wrong. So the partitioning should be done based on different criteria, right? Not based on whether the person is academic or non-academic. So maybe we can divide the staff into a group of staff depends on their, for example, staff number, for example. So maybe we take only the first 1050, give it to one thread, and the second 1050 we give it to the second thread, no matter whether they are academic or non-academic, in order to maintain the load balance. Okay, so the design of the thing, or the design of the program, is very critical process actually, that will affect later the result of your program. So if we divide it based on academic and non-academic, and the academic are only 100 and the non-academic are 2000, actually the program will work. The result or the time needs by the parallel program actually is almost equal to the sequential program, because we saved only the time of 100 staff only. The other 2000 staff are still working in sequential mode, right? So this is what happened if we don't distribute the load equal. Okay? How to achieve load balance? Equally partition the work each task receives. So you give the workload to tasks in equal manner. You divide the workload equally among the tasks. Okay? Then here, use dynamic work assignment. So if you can use the dynamic work assignment, so if let's say one task finished and the other tasks still have a lot of work to do, then the program supposed to be, in this case, the program supposed to be smart enough to detect that problem, and should be smart enough to take or create another, or divide the existing workload and send another chunk to the processor that already finished. So in this case, the program is called to be dynamic work assignment, or it's called to have the ability to reassignment work dynamically. Okay, so it depends on the idle time, the program will rearrange or reassign the workload among the processors. Okay, then we have the agenda here. Granularity. Granularity I already explained before. So guys, we will stop here. We will stop on the granularity. So hopefully, inshallah, next week we finish all of that stuff, because we almost finish. Next week we will try to take an example by code of how to consider the granularity, if we could get time. And inshallah, I will leave you with your assignment. And also tomorrow we have the test too. Inshallah, I hope that you all ready for the test. Are you ready, guys, for the test?
Inshallah.
Okay.
Inshallah.
Good. Okay, then that's all. If you don't have any question,
Sir, so I
Yes.
got one last question. So,
Yes.
I mean, where is the range of the test, I mean, until which chapter and from which chapter?
What do you mean?
I mean, what's included in the test?
Test 2.
Yeah.
I already explained this last week. You was not there, maybe.
All right. Sorry.
Okay. Let me stop recording first.